So with all these, remember, it's just a simple equation. So combine your like terms and then solve. So let's do number 1 first. For number 1, they give us 2x plus 3x plus 5x equals 180. So let's combine our like terms on the left. We've got 2 plus 3 plus 5, that's 10x. And it equals 180. And all we have to do from here is just divide, right? So yeah. Hey, Natron, do me a favor and mute me for me, please. Thank you, sir. Appreciate it. All right. So yeah. So all you're gonna do is you're gonna combine your like terms. 2, 3, and 5 make 10, right? So you got 10 x's. So you 10x equals 180. Divide by 10, you get 18, and that's your final answer. And then it's the same thing with the other ones. Just combine your like terms where you can. You got a 3x and a 4x. These are like terms. The 20 is not. But if we do this, 3x plus 4x, we got 7x plus 20 equals 50. And it's a two-step equation. These are real easy. We just either add or subtract the number by itself and then divide by the number on the x, right? So here, this is a plus 20, so we subtract 20. $50 minus 20 is 30. And so we're left with 7x equals 30. And what we're going to do is we're going to divide. And we're going to say to ourselves, well, wait a minute, that doesn't come out nice and even. 30 divided by 7 is like kind of somewhere around 4.5-ish, maybe 4 1/3, but it's not exactly that. It's kind of an ugly number, right? It's 4 2/7 to be exact. And so in situations like this, all you're going to do is you're going to look 30 and 7. Hey, can I simplify? Is there a number I can divide both 30 and 7 by? And you know the answer to that is no. Not other than 1, and that doesn't matter. So if it was me, I would just leave it as 30 over 7. You know, there's no reason to do any more than that. If you really, really, really want to have a mixed number, you can do 4 2/7, but honestly, this answer right here is superior in every way, you know? All right, last one. We've got 2x minus 3 plus 5x plus 2 equals 70. So once again, combine your like terms. No worries. Combine your like terms. Right, you've got a 2x and a 5x. That makes 7x. You've got a negative 3 and a positive 2. That makes negative 1. And that equals the thing on the other side, 70, right? So we're going to solve for x. Add 1 to both sides. And we divide both sides by 7 to get rid of the x, right? And here's the thing. Like, again, 71 divided by 7, that's close to being even, but it's not exactly even. So I would look, well, 71 and 7, you can't divide 71 by anything that you can divide 7 by, and vice versa. So therefore, we're just going to leave it like this. Don't try and do anything fancy. I know it's 7.1 something, but you don't need to do that. Just if you're really, really, really feeling like this needs to be broken down more, you can give that. But again, right here, that's the superior answer, and it's also easier to get, right? You're not gonna do it here and not have already gotten this answer. So I'm gonna tell you honestly, there's no point in getting this. Leave it here. Anywhere that this would be correct, this would be correct, and this is easier to get. So just be aware of that. Those improper fractions, they really are your best friend. I'm not saying that it's wrong to do 10 and 1/7. It's not. It's fine. It's great. But this honestly requires more work than this does. So why do this when you can do this? You know? Okay. Let's push forward. Bloop. So what are we doing today? We're going to use the triangle angle sum theorems to solve problems involving the angles of triangles. How are we going to do this? We're going to use the angle sum theorems to find missing angles. There's going to be one really nice big example to do today. And we're going to go over that in a bunch of different ways. Because I want to tell you, there's like 1,000 different ways once you have these two together to get a bunch of your answers. And it really, really, really does mean that you've got a lot of ways to go. And, it's going to be about what you see first. If you see one way first or you see the other way first, great. The other thing I want to sort of caution each and every one of you in this room about is the fact that there is no formula for this sort of stuff. Just like with the angle sum stuff and the segment addition postulate and the angle addition postulate, like there's no special formula to doing these. Like you're not gonna look at and you're gonna plug stuff in, and then you're gonna get an answer. It's all about thinking. And if you don't think, it's not gonna be good. So make sure that you're thinking through and asking yourself, okay, what do I know? How can I figure stuff out? Because I'm telling you right now, some of you are going to be looking at this and you're not going to see what to do immediately. And that's okay. You're going to really literally just have to sit there and knock some dust off your brain and just do it. I promise you that these are the sorts of things you think about and think about and think about, and then you're going to get it. But you're not going to have like this special formula you go to just to sort of cookie cutter your answer, because there's going to be all these different pictures and all these different shapes and all these different sizes. And you're just going to have to think. And I know that's uncomfortable in the beginning, but it's what you got to do. So let's talk about the parallel postulate. So the parallel postulate is sort of how do I say this? It's really the foundation of what we do. The parallel postulate says that through a point not on a line, so here's your point, here's your line, and the point is not on the line. And through this point, there's only one line that you could ever draw that is parallel to this line. So what? Who cares? Well, on one hand, this is actually the reason for our ability to do what we do here. Everything. Back in the day, you had people thinking about this. This is way back in ancient Greece. This is one of the things that Euclid, the ancient philosopher / mathematician, this is one of the things that he observed to be true. He in his big book called The Elements, he just said, "Hey, this is what it is. If you've got a line and you've got a point over here, there's going to be only one line that you could draw that's parallel to it." And that feels pretty intuitive. And then much later on, as we get into the 18th and 19th centuries, and even into the 20th century, we had people saying, well, okay, but we need to be able to break all this stuff down and get it down finer into things so that they're usable. We want to make everything sort of as the term we use in mathematics is elementary as possible. Elementary meaning into its elements, not necessarily easy, but elemental, right? Think about more like chemistry. You know what I mean? But you go through, and a lot of the things that Euclid observed as just fact, he created postulates, right? Things that we look and we observe and we say, yeah, that's true. Yeah, that's fair, that we don't need to argue about this. And they broke a bunch of them down. They said, all right, well, yeah, we could say that this is just true, but why? Let's break it down and see if we can prove that it's true. And a lot of the things they were able to do that with, but not this one. They tried really, really hard to break this one down, and they couldn't. And the reason is, well, first of all, what they tried to do was like actually constructively prove it, and that didn't work very well. They couldn't just go through and say, all right, well, given there's a line, there's a point, let's prove that there is one and only one line parallel. And they couldn't. Especially once they broke everything down into more elementary ideas. They didn't have the tools to be able to prove it. And when mathematicians run out of ideas on how to do stuff like that, a lot of the time what they'll do is they'll try and create contradictory statements. They'll say, all right, well, let's say it's not true, and then they'll show that this statement not being true makes a big mess and it causes problems that we can't have, right? But the thing was, they tried that and it just created a different branch of mathematics. I'm sure some of you in your existence as humans have heard of non-Euclidean geometry. So when this is true, we are working in what we call plane or Euclidean geometry. Like planes on a flat surface. And so they went through and they were like, all right, well, let's presume that no parallel lines could go through this point. And they went through and they worked through it, and they realized what they had created was geometry on the surface of a sphere. When you're on a sphere, a line is defined as some kind of equator on the sphere, something that cuts the sphere exactly in half. And if you notice, I've got 1, 2, 3 different equators. There's no way to draw 2 equators so that they don't touch. On a sphere, there are no parallel lines at all. And then they said, all right, well, we tried that. Now what do we do? And so what ended up happening is they tried going the opposite way. Well, okay, what if there's multiple? What if there's many parallel lines? What then? And they ended up, by doing that, creating what's called a hyperbolic geometry. Now you'll talk about parabolas and hyperbolas and all those eventually, but imagine for a second like sort of a saddle shape. Here, I'll draw like a really, really bad saddle. We'll see if I can do it. It won't be good, but we're gonna try. Not bad. Not bad. Imagine a shape like this. So again, a line is just, let's say here's a line, right? Let's say I pick a point up here. I can make as many different parallel lines as I want. There's one here. There's one here. There's one here. Like you can make as many parallel lines as you want. Because remember, the only thing that matters is that they don't touch, right? The only thing that matters is that they never ever touch. So who cares who cares where they go as long as they don't touch? So this there's an infinite number of parallel lines. So we got geometry on a sphere, geometry on a hyperbolic plane is what this is. Um, but we're not going to be doing these. These are kind of wacky sometimes. We are focused on the plane, a flat surface, if you will. And so what we are going to do, just like Euclid in ancient Greece, is we're going to only be concerned with the situations where this is true. And not only does that make things easy for us, it also means that we don't have to worry about like trying to deal with silly things like working on a sphere. All right. So now let's get because the reason I want to take the time to talk about this is that this only works on a flat surface. I mean, I'm sure some of you have heard before that three angles of a triangle add up to 180. Yes, on a flat surface. This is the point in time where there's a globe in my classroom. I would take a dry erase marker and a globe and draw a triangle that has three 90-degree angles because you can on a globe because the angle sum theorem doesn't apply. So just be aware, we are talking about on a flat surface only. So here, the angles of a triangle, when you add them all up, make 180. Now notice this is theorem. So the thing of it is, you can prove this. You can prove this. And it's actually a very simple proof using what we just did. You're going to take a line in a triangle. Step one is to draw a line parallel to the base of the triangle. And then you say, all right, well, wait a minute, hold on. I've got stuff here now. This angle right here and this angle here, alternate interior, so they better be the same. This angle here, alternate interior, so they'd better be the same. Can't count. That should be 4 and then 5, right? And so, well, wait a minute, hold on. 2, 5, and 4. These angles make 180. Measurement, measurement, measurement. But wait a minute. Angle 2 and angle 1 are the same. Substitution. Angle 4 and angle 3 are the same. Substitution. Ta-da! We win. We get it. So the thing of it is, these three angles have to add up to 180. The other thing that we're going to be talking about in this section is called the triangle exterior angle theorem. So the idea is that we made an exterior angle. We took the triangle and we took the bottom side and we sort of just pulled it out. This angle that's created out here, angle 1, is the same size as angle 2 and angle 3. Why is that? Well, think about it. These three angles on the inside add up to 180. These two angles add up to 180. This plus this, let's call that angle 4. The measure of angle 1 plus the measure of angle 4 is the same as the measure of angle 2 plus the measure of angle 3 plus the measure of angle 4. Well, wait a minute, I've got an angle 4 on both sides, so I can just cancel that out. Ta-da! So that's the thing. And here's the one thing I will tell you. 9 times out of 10, you're not going to get the type of information where you're going to be forced to use one or the other. It's just really hard to do because these two theorems are very, very closely based on each other. If you'll notice, we actually use this theorem to prove this theorem, right? We have to know that these three angles add up to 180 to be able to produce the exterior angle theorem. So 9 times out of 10, with some creativity and some hard work, it doesn't matter which one you use, you can get the answer all the same. Now, that being said, some of you are going to see one way versus the other way, and that's fine. I'm not going to tell you which way you have to do because you're going to get the same answer regardless of which way you go as long as you do good math, right? So let's get on to it. Some of you are going to be able to look at this already and go, okay, well, I can do this. What I want to do is I want to give you 2 minutes to just sort of noodle your way through this and see if you can figure it out. Like I said, there's about 1,000 different ways to go about doing this. I'm not telling you that one way is better than the other, but I am telling you that you need to think about what you have and how you can use it. So go ahead, give it a try. Okay. So, like I said, there's about 1,000 million, billion, zillion different ways to go about doing this. And it basically boils down to what do you want to find first? Do you want to find X first? Do you want to find Y first? Do you want to find Z first? You can do it regardless of which way you want. Let's start with X. I'm going to find X without using any of the other things. X is probably the easiest one to find first. Because look, here's this little tiny triangle right here. Remember, the angles add up to 180, right? So this angle, and this angle make 180. 43, 59, and X had better make 180, right? Angle, 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 right? Well, let me combine my like terms and solve. What do we have? We got 102, right? So we got X plus 102 equals 180. Subtract. Sure. That works. But now, what if I wanted to find y before I found anything else. Let's see if I can do it. Well, look, y is an exterior angle to these two, right? So whatever y is, it had better be the same as these two. Yeah? Right? Whatever y is, it has to be the sum of these two remote interior angles. So let's add that up. 59 plus 43. That's I think I screwed up earlier, didn't I? 70. Yeah. Gotta be careful. It's easy to make mistakes. 10 minus 2 is 8. Okay. All good now. And here's the reason why I noticed that I made that mistake. Is because what do you know that x and y have to be equal to? Right? They make a linear pair together, so they better add up to 180, right? So anyway, going back to it, 43 and 59 better equal y. These two remote interior angles had better add up to the exterior angle. So you get y equals 102. Pretty easy. So now what about z? Again, I don't want to use x and y. I could do that, but I don't want to. Well, look. With z, you could use this whole big outside triangle. So I know all the angles of this triangle, right? I know this one's 59. I know this big angle B, ABC, is composed of this angle that's 43 and this angle that's 49. So I could do this too, yeah. So let me make ABC without all the extra distraction in there. This is Z. This is 59. 43 and 49 is 92. So once again, what do the three angles add up to in a triangle? 180. So let me do that. Z plus 59 plus 92 equals 180. Combine my like terms. Z plus 151 equals 180. Subtract 151, and I'm going to double check my work this time. 29. 180 minus 150 is 30. Minus one more is 29. And again, I chose to do each and every one of these in a different way. That's what I chose. But here's the thing, you don't have to. Right? If you know what x is, you don't need to use this triangle in exterior angle sum theorem. You've got this. If you know x is 78, y is definitely 102, right? They better add up to 180. If you know y is 102, you can use this triangle instead of the other one, right? 49, 102 had better make 151. 151 from 180 is 29, right? It doesn't matter. As long as you do good math, it doesn't matter what you do. Here, I got you one better. You could even go the opposite way. You could say, all right, let me find z first. Z is 29. Oh, well, wait a minute. Hold on. 29 and 49 make 78. So that's what 78 from 180, that's 102. That's what y equals. And then how do I find x? Oh, I can do z and 49, add those up because this is the exterior angle. These are the two remote interior angles. And I could get 78. There are 1,000 different ways to do this. You're only going to be limited by your creativity. So make sure that what you do is one, good quality math, and two, something you think about. Because I'm telling you right now, if you don't let yourself think, if you don't try to do it with some thought behind it, it's never going to get done. There are no just sort of simple, quick, easy things here. It's just thinking. Now, once you have sort of gotten the flow of it, the thinking gets easier. But unless you're willing to think, some of these problems are never, ever, ever going to get done. There's one in particular that I'm thinking of where it's got like 6 different parts. It's like an A, a B, a C, a D, E, F, and a G, where it's like having you find all these different angles in there. There's there's no one right answer to that one. I mean, each angle is set. You're going to get the same, you should get the same thing I do, but there's no correct process. There's so many different ways to go about doing all this stuff. You're going to have to do it. And I guarantee you something like that I'm going to put on the quiz because I need you responsible for thinking, period.